Hey guys, welcome back to week 6 of my series where I'm learning ML through an optimization perspective. So this week I finished chapter 2 of the convex sets from the Boyd book. So this week I spent only about 6 hours studying this week. Um, Also, sorry for no video last week. So we traveled to Vietnam and we were in Ho Chi Minh, Da Nang, and Hoi An. So now I'm back in Japan for another week before I return to the USA. So I just wanted to share a short video of our time in Da Nang. So on screen is video from our hotel in Da Nang. So this week I wanted to do something a bit different. So last week I covered dual cones and generalized inequalities, but I didn't have time to go through the dual characterization of the minimum and minimal elements, which is actually a very important application. So I'm going to cover that first today. Then what I'm going to do is I'm going to walk through one of the problems from the chapter. So problem 2.9 on Voronoi sets. So I really like this problem because it touches on a bunch of fundamental concepts, polyhedra, half spaces, supporting hyperplanes, and like geometric intuition. Plus, Voronoi diagrams actually show up everywhere in ML. Let's get started with a quick review of dual cones, then let's dive into minimum and minimal elements. So before jumping straight into the minimal and minimum elements of a set, I'd just like to review the fundamentals from last week, which were about dual cones. So given a cone K, the dual cone K star is defined as follows. So K star is the vectors y such that the inner product between that y and any x from K is positive. So it's just all vectors y that point in a similar direction to all vectors in K. We also saw that generalized inequalities can be characterized using dual cones. So what that means is that when we say that x is less than or equal to y under the dual cone or the proper cone K, then that's entirely equivalent to saying that there's some lambda, or for all lambda in K star in the dual cone, lambda transpose x is always less than or equal to lambda transpose y for all lambda in K star. Okay, so let's use this to understand minimum and minimal elements. Okay, so before we dive into the definition, let me explain why we even need two different concepts, minimum versus minimal. So in ordinary optimization with real numbers, so on the set R, this distinction doesn't actually matter, they're the same. So if I ask, what's the minimum of the set that contains, let's say, the numbers 3, 5, 7, 2, and 9, you can tell me that the answer is clearly 2. It's the unique smallest element, everything else is bigger. So in other words, the set of real numbers has a total ordering. We can always compare the elements. However, in the general proper set, case K, we might not always be able to compare elements. So consider the example in R2 with component-wise ordering with K is a positive set of R2. So the question is, can we compare the points 3 and 1 and 1 and 3? Well, it turns out no, because we can show that neither one is less than or equal to the other. So just to be clear, the point 3, 1 is not less than or equal to 1, 3 under the R2, nor is 1, 3 less than or equal to 3, 1 under R2. So let's just take a second to think about why. So the answer is obvious, but it's important to understand the underlying reason. Why is 1, 3 not bigger or equal to 3, 1? Well, the answer is because if you move this one over there and you say is 1, 3 minus 3, 1 still in the set R2, positive set of R2. Well, if you do the subtraction, you get the point negative 2, 2, which is, over here. But of course, this point is not in the positive set. And so therefore, this inequality does not hold under the positive R2. So this is actually why we need two different definitions for minimum and minimal. Minimum turns out to be a point that's less than or equal to everything else. So it's a global notion. On the other hand, minimal is a point with nothing strictly below it. So these are two different concepts in the generalized inequality due to this very reason that sometimes we can't compare elements in the proper cone. So in total ordering sets like the positive reals, these are the same, but in partial ordering sets, they can be different. So let me show you exactly what I mean by the definitions. Okay, on screen here is a definition for the minimum element of a set under the cone K, under the proper cone K. So x is a minimum if and only if y is greater than or equal to x under this cone, or proper cone, for all y and s. So what does that mean? Well, that means that, this is, given the implicit assumption that y is actually comparable to x for all y and s. So that means is that x is less than all elements in S, but also that all elements in S is also comparable to x as well. So this is a very strong condition, right? So for x to be a minimum, every element that, y in the set S must satisfy y minus x is in the set K. So geometrically, this means that the entire set S must lie in x plus k. So just as an illustrative example, pretend that x is in the set S. I know it's not the case here, but let's just pretend that it was. Then, just geometrically, we can see that x is indeed the minimum element. Why? It's because all the elements that are comparable to it in R2 in this case, so the set K is R2, is to the right and above this element. So one more property of the minimum element of set is that if a minimum element exists in the set, then it must be unique. So we can reason our way through why that's true. So I'm just going to talk through the argument, but hopefully it makes intuitive sense. So I'm going to assume that there exist two different minimum, but then show that they must be the same. So hear me out here. So if both x1 and x2 are minimums, so since x1 is a minimum by definition, we know that x1 is less than or equal to x2, because of course x2 is also in the set. Likewise, since x2 is a minimum by definition, x2 must be greater than or equal to x1, since of course x1 is in the set. So this means that x2 minus x1 is in K, and that x1 minus x2 is in K. So for a proper cone, of course this implies that x1 is equal to x2. And so we've shown that if there's two elements that are minimum of the set, then they must be actually the same element. But here's the thing. There's many sets, and we'll show some later, that don't have a minimum. Even if they're bounded below, they don't have a minimum. So just quickly, pretend that this is really our set S, and that x is not in the set. Just ignore this element here. If you pick any x along this bottom curve here, and you ask the question, is x the minimum? Well, take this point here. is it comparable to this point there? Well, by the same argument we showed earlier, no, they're not comparable, because this point, this point above, has a lower, more negative first coordinate, but it has a higher second coordinate, in the up direction. On the other hand, this point over here is not comparable to this point with the same reason, because the coordinates increase and decrease separately. So actually this, circles don't have a minimum element. Okay, since we finished talking about minimum elements, we can talk about minimal elements. So the point x in the set S is a minimal if and only if there's no other point in S that is strictly less than x. So what that means is that for some y in S, if y is less than or equal to x, then it's the case that y must be equal to x. Okay, what does that mean? Well, notice what we're saying here. We're not requiring that x be comparable to everything. We don't have, for all y in S. We're just saying for the y's that are in S that are comparable to x, then it must be the case. Okay, so does that make sense? So another way of thinking about it is, let's draw a diagram. So pretend that there's a circle with x on the edge. And so we ask, is x a minimal element? The answer is yes. It's because for all the elements that are comparable to x, yes, it turns out that there are no elements in x which are less than it. Indeed, the only elements that satisfy this inequality, such that y is less equal to x, that's only the case when y is equal to x, right? And so, in other words, the cone here, so the point x minus the proper cone k is the points that you're looking for to disqualify the point x from being a minimal element of S. So unlike a minimum, a set can have many, many minimal elements. So we can see that here, right? We already showed that a point here on the bottom left of the circle is not comparable to other points on the other side of the circle. However, if you pick a point here and you ask if it's a minimal element, so you're only looking at points which are comparable to this point. And those points are over here, right? In this 90-degree orthant, centered at x. And so you're looking for any other points in this area which satisfy that requirement. And of course, since it's a circle, there's no points over here. And so indeed, this point on this side of the circle is a minimal element. And you can show that every single point, right, every single point here is a minimal element. So circles actually have infinite number of minimal elements. And remember that we showed that circles don't actually have minimum elements, but they do have an infinite number of minimal elements. So just in summary, the minimum element of set is comparable to all elements. It's unique and it's a strong condition. The minimal element is just comparable to everything. Is nothing less than this element, such that you're comparing it to something that's actually comparable. You can have many elements which are minimal, so it's a weaker condition. Indeed, you can show that if an element is minimum, so there's only one, then it also must be minimal. But of course, if something is minimal, that does not imply that it's minimum. Okay, so you probably already anticipated this, but we're going to use dual cones, so this K star over on the left side. to characterize minimum and minimal elements as well. And so K star shows up everywhere, right? I'm getting used to this, but I'm sure I'm gonna love K star. So here's the dual characterization of the minimum element. So the one that's unique. So the characterization is as follows. So when X is a minimum of the set S, what that means, or equivalent way of saying it with the dual cones, is that for all lambda in the dual cone, and for all y in the set S, it is the case that the inner product between lambda and x is less than or equal to lambda and y for all such elements, provided that lambda is not equal to 0. So why does this work? Well, the argument is actually pretty simple. So if y is greater than or equal to x, this is the same as, of course, y minus x being in k. But by definition of the dual cone, we take some lambda for the dual cone, and we take the inner product with some element in k. In this case, that's the difference between y and x, and we take the inner product, and we set that equal to greater than or equal to 0. Right, we're just applying this formula here. And we can do some distribution and move this side over this side, and we arrive at our expression. So very simple. Okay, so geometrically, what this says is that x, so x is the minimum. This says that x minimizes every linear function, so lambda over some function over s. So geometrically, what x is a minimum is really saying is that x minimizes every linear function, so lambda transpose x for any lambda in k star. So any linear function that takes x and takes the transpose, right? So x minimizes every linear function over s, where lambda is in the dual cone. So this is incredibly powerful. So instead of checking the geometric condition, remember from the last interpretation, from the dual cone, from the regular cone, we can check many optimization problems. Does x minimize lambda transpose y over y is in S for each lambda is in k star? So this also connects beautifully to supporting hyperplanes. So just bear with me. I know that the set S does not actually have a minimum, as we just discussed, but pretend that x really is the minimum. Okay, just bear with me here. So when we see that lambda transpose y minus x, in this case z minus x, equals 0, remember that's the equation of a hyperplane. So the hyperplane is a supporting hyperplane to S, and so that every element in S is on the right side, of this hyperplane. It's a little bit offset in the picture, but hopefully you get the idea. So the half space lambda transpose z minus x is greater than or equal to 0 contains all of S. So since this holds for every lambda in the dual cone, the set S is contained in the intersection of all these half spaces. So in other words, if X is a minimum set, then S must be a subset of X plus K, where we're doing, element-wise addition here. So this is exactly the geometric condition of X to be a minimum we saw earlier, right? So now we have three equivalent characterizations for the minimum element of a set. So the first one being obviously that the set is set S is subset of X plus some offset, which is the cone. So that means that X must be, on the bottom left of the set. And then the second way is an optimization perspective, which is that X minimizes all linear functions of X for lambdas in the dual cone. Lastly, we have the hyperplane interpretation, which is that all supporting hyperplanes from K star support S at X. Okay, so moving to minimal elements, the characterization is slightly different. The point X is a minimal element of S if and only if we have the following. X minus K intersect S is only the point X. So in other words, if you go down, so down and left of point X, then the only point which is, satisfies that, which are still in S, is only the point itself. So this is the same idea, just, geometrically, what's happening with minimal elements. All right, y is less than equal to k, so comparable, so it must be left into the below, and y is, in S, only if y is equal to x. So we saw earlier visualization of that, and here's just another one. So x here is a minimal element because there's no points in S which are to the left and below as well. And by the way, I believe this is an incorrect diagram. It should be 90 degrees here. So K should be sort of the negative orthants. Okay, anyway, so how do we actually characterize X being minimal element of S using dual cones? So how we do that is we say that the same idea, this is a direct copy from the minimum element, which is that the inner product between lambda and X is less than or equal to lambda and Y for all Y and S. But the key difference is that this only holds for some lambda in K star, not for all lambda. And we also require that lambda is not equal to 0, similarly as the minimum element. So notice that this word is the only difference, really, between the definition, some lambda and all lambda here. So what this means is that X is a minimal element if there exists at least one linear function, lambda transpose X, such that X minimizes over S. So there's at least one direction, in other words, in which X is optimal. So note that this is a much weaker condition. We only need one supporting hyperplane from K star, not all of them. So I'd like just to walk you through an example of minimum and minimal elements and finding those of some set S. So consider the set S, which is just the positive vectors such that the component-wise multiplication must be equal to 1. And so if you plot what that looks like, it's a hyperbola with a line that looks like this. Is there a minimum? And if it is, what is it? For a point to be a minimum, the entire hyperbola must lie in that point plus the positive R2. But wait a second. If we pick any point A and 1 minus 1 divided by A, so the multiplication is equal to 1, if we move to some point x1, we can always find another point B, so B and 1 minus B, where B is less than A. So there's no single point that dominates everything. So therefore, there's no minimum of this set. Okay, but what about minimal elements? So let's take a point, again, A 1 over A on the hyperbola. We ask, is it a minimal? So remember, we have to find some lambda in the dual cone, which in this case is R2. And remember, R2 is self-dual. So K and K star is the same. And lambda is not equal to 0, such that the inner product between lambda and A and 1 over A is less than or equal to lambda transpose Y for all Y in S. Okay, so since we just need to find a single lambda, let's try when lambda is equal to 1 over a. So sort of the opposite of the point x here. So then the inner product is equal to this, and the sum is 2. So for some other y in S, let's call it b1 over b, then the inner product between lambda and y is b over a plus a over b. But by the AMGM inequality, we know that b over a plus a over b must be greater than or equal to 2 times square root of the multiplication together, which of course equals 2. So in other words, for lambda equals 1 over a, we've shown that for this particular lambda, the inner product between this lambda and some point, so a 1 over a, is less than or equal to lambda transpose y for all y, remember, because y was some b, just some arbitrary b in 1 over b. So in other words, we've shown that any point a 1 over a is a minimal element of the set S. So in other words, again, any point in the hyperbola is also a minimal element of the same hyperbola. Geometrically, this means that at each point a 1 over a, the hyperplane 1 over a times z1 and a z2 equals 2 is tangent to the hyperbola. So this point here. So that is the supporting hyperplane. The hyperbola lies entirely on one side of it, and the direction of k equals positive orthants. But of course, notice that different points on the hyperbola have different supporting hyperplanes. There's no single supporting hyperplane from which all directions in k star that works. So this is why that there's no minimum, only many minimal elements. Alright, so that wraps up minimum and minimal elements. So let's shift gears and talk about what's called Voronoi regions, which will give us another perspective on polyhedron and supporting hyperplanes. So this is problem 2.9 from the textbook. I'm just putting it here just to walk through a slightly more involved example. So here's a setup. We have k plus 1 points in n-dimensional space, so x0 all the way up to xk. So the Voronoi region around x0 is defined as the set of all points, so the distance here, that are closer to x0 than to any other point. So hopefully that should make sense. So in this region on the right, the Voronoi region should be shaped something like this, right? So just visually in two-dimensional space, if I pick any point in this region, so here, x0 is its nearest neighbor among all our points. If we draw half planes in between x0 and each point, sort of like so, then whatever values are inside this region should be the Voronoi region. So based on this little exploration, we have some intuition that the Voronoi region can be described by the intersection of such half spaces. So part A asks us to show that this is a polyhedron and express it in the form ax is less than b. Part B is the converse. So given a polyhedron, can we find points that generate it as a Voronoi region? Finally, part C asks whether any polyhedron decomposition can be realized as a Voronoi diagram. So spoiler for this last part, the answer is no, and we'll show why. So let's start with part A. To show that the Voronoi region is a polyhedron, we simply need to express V in the form of x such that ax is less than or equal to b. And remember that polyhedron is simply the intersection of half planes. So if we can show that each individual constraint of the Voronoi set is a half-space, then V is just the intersection of k half-spaces, which by definition makes it a polyhedron. So let's take a single constraint and do some algebra. So we want to show that the constraint for a given x for the Voronoi region is the same as the constraint for the half-space. So that is, given x such that this inequality is true, we want to find an AI and a BI such that this inequality is also true. So let's start on the left side with some algebra. Since both sides are non-negative because it's a norm, we can square both sides. So when you square the 2 norm, that gives you the transpose times itself. And so we just write that out. And once we expand this expression, we get as follows. So notice that the x transpose x on both sides cancel each other out. So this is a key step. So here I just cancel the x transpose x, and then because of the this property here, when you have x transpose x, that's simply just the square of the norm, second norm, and so I just wrote these as follows here. And then we could rearrange this inequality as follows. Okay, and then notice this form here. This actually resembles this form here that we wanted to get to. We have the AI transpose x, so in this case, AI is 2 times xi minus x0. And we have BI, which is this value here. And so this equation represents a half space. Okay, then just writing out the full matrices here, we've shown that the Voronoi region is simply just the intersection of all these half spaces. So let's look at these AI and BIs again more closely. So what is the geometric meaning of these parameters here? So actually what this represents is the perpendicular bisector between x0 and xi. Okay, so what does that mean? What that means is that you first draw a vector pointing from x0 to xi. So the vector is defined as xi minus x0. And then what you do is you draw a perpendicular bisector along the line, and this line is a half space. So the normal vector to this hyperplane is 2xi minus x0, and this points from x0 to xi. Alright, so moving to part B flips the question around. So we're given a polyhedron P this time with a non-empty interior. So we want to show how to find x0 or xk. So we need to construct the points x0 and xk such that P is a Voronoi region of x0. So I think this is cool because it shows that the relationship goes both ways, at least for individual regions. We'll see in part C that there are limits when we consider full decompositions. Okay, anyway, so since P is a polyhedron, we can write it as follows. Right, this is just the intersection of half spaces. So these AIs are the outward pointing normals for each face here. Okay, from part A, we know that the Voronoi constraints have the following form. So our strategy is we want to match the polyhedron constraints with the Voronoi constraints. So here we're given some x such that AI transpose x is less than or equal to BI. So we want to find x0 and xi such that these constraints are also true. So here's my solution. Here's how we construct all these xi's. So the first step is to pick any x0 to be any point in the interior of P. So this is possible because remember P is a non-empty interior. Okay, now for each half-plane I, construct xi by moving x0 in the direction of the outward normal. So why would we do this? Well, think about what we need. We need a perpendicular bisector from x0 and xi to be the ith face of P. So notice from part A, we saw that the perpendicular bisector has a normal vector proportional to xi minus x0. So for the perpendicular bisector to align with the face I, we need xi minus x0 to be parallel with ai. So what does that mean? Well, in this picture, ai is pointing, let's say, this direction here, right? Pointing downwards and to the left. And xi, so xi's would be here, right? And x0 is here, so that's this point there. So we need them to be parallel with each other. So we need xi minus x0 to be parallel with ai. And so this naturally leads to the following equation. So since they're parallel and they are overlapping, the vector xi minus x0 is just some proportion or some multiple of ai. So we can rewrite this as follows. Okay, so this alpha here, so this is chosen to make the constraints match exactly. So we're placing each xi outside P along the outward normal direction from x0. So now we need to find the right proportion or right multiple, the right distance, alpha I. So in other words, taking a look at these Voronoi constraints, we want to match these with the polyhedral constraints. And then we can plug in this value for xi into the Voronoi constraints. Okay, simplifying this inequality here, we get the following inequality. So notice that we have the ai transpose x, which matches what we want here on the left-hand side. So to make this right-hand side correct, we need to set this equal to bi. And then once we do that, we solve for alpha I. Okay, and we get the following result here. So here's a key observation. Since x0 is in the interior of P, we have ai transpose x0 is less than b. So this is not less than equal to b. This is a strict inequality. So what that means is that alpha I must be greater than 0. It can't be equal to 0. So this means all our xi points are well defined. Okay, so part C is a little bit more of a setup. So it's a long word problem, but essentially part C introduces the full Voronoi decomposition. So instead of the region just around x0, we consider all regions. So Vk is all x in Rvan, such that we have the points which are closer to xk compared to any other points. So notice that these regions, V0 through Vk, partition all of Rvan. So they're all polyhedral with non-empty interior. They cover everything and their interiors don't overlap. So the question is, suppose we have some other polyhedron decomposition in Rvan. So just some collection of polyhedron like P1 through Pm that partition the space. So the question is, can we always realize this as a Voronoi diagram? So the answer is no, and we're going to prove it with a counterexample. So consider this decomposition in R2. So let P1 be the upper left wedge. So this is y is greater than 0 and y is greater than x. And we have the lower half plane, which is y is less than or equal to 0. Then we have the upper right wedge, which is y is greater than or equal to 0 and y is less than or equal to x. So notice that all regions meet at the origin. So the boundaries are as follows. So let's prove that this cannot be a Voronoi diagram. So suppose for conjugation that this can actually be a Voronoi diagram. So that is, this is a this is generated by points A1, A2, and A3. So a perpendicular bisector has a normal vector parallel to A1 minus A2. So for the x-axis, the normal is 0, 1, so here. So it's pointing in the y direction. So therefore, A1 minus A2 must be parallel to 0, 1. But wait a second. What this means is that A1, A2 must have the same x-coordinate for it to be the difference of 0. So we have the same logic between the boundary of P3 and P2. The positive x-axis is the perpendicular bisector between A2 and A3. So again, that means that A2 and A3 also have the same x-coordinate. So what this means is that all 3 points lie on a vertical line. Okay, so let's look at the constraints. Okay, so let's look at the boundary between P1 and P3 now. So this is a line y is equal to x. So the line y equals to x has normal vector 1, negative 1, right? It's perpendicular to the direction 1, 1. For this to be a perpendicular bisector of A1 and A3, we need A1 minus A3 to be parallel with 1, negative 1. But wait a second, we have A1 minus A3 is 0 minus, or 0 comma y1 minus y3. So for 0, y1 minus y3 to be parallel with 1, negative 1, we need 0, y1 minus y3 to be some multiple of 1, negative 1, for some lambda equals 0. But lambda can't be both 0 and non-zero at the same time. Therefore, this polyhedral decomposition cannot be realized as a Voronoi diagram. Okay, so what's really going on here? Why can't arbitrary decompositions be Voronoi? So the issue is that Voronoi diagrams have rigid geometric constraints. So each boundary, remember, must be a perpendicular bisector. So this is a very specific type of hyperplane. And when multiple boundaries meet at a point, the angles in relationship must be consistent with the actual Euclidean distances. So in our counterexample, the 3 boundaries meeting at the origin force the generated points into a vertical line, here. But when the 3rd boundary constraint becomes impossible to satisfy. So I thought this was a really cool example of how metric geometry constrains combinatorial structure. The Euclidean distance function isn't flexible enough to generate every possible way of partitioning space.
Alright, so that wraps up the content for this week, but I wanted to talk a bit about what's coming up next. So my original plan was to move straight into chapter 3 on convex functions next week, but honestly I think it makes more sense to spend one more week on chapter 2 and work through some more of the exercises. So the reason is that there are a lot of really good problems in this chapter that I haven't gotten to yet, and I think doing a few more will really solidify the concepts before moving forward. And I happen to know that these concepts that we learned in chapter 2 are super fundamental to everything else we do later. So plus I'm still in Japan now and still busy with work. So, but I'll be returning to the US in about a week. And I think once I'm back home and settled in my normal routine, my pace and intensity will pick up quite a bit. So anyways, next week, week 7, I'll be going through more problems from chapter 2. I'm thinking probably some of the ones on operations that preserve convexity, maybe some generalized inequalities, or maybe even a really, really difficult problem of some sort. So I haven't really decided exactly which ones yet, but I'll pick problems that cover different aspects of the material. Then, starting week 8, I'll dive into chapter 3 on convex functions, which I'm really looking forward to. It's where a lot of the optimization theory really starts to come together. So anyways, thanks for watching this week. If you have any suggestions for which chapter 2 problems I should cover next, feel free to leave them in your comments. So I'll see you next week.